So, hello everyone. Welcome to today's live discussion session on geology and soil mechanics. So, in today's class, we will be mainly discussing the topic of consolidation. So, in the previous class, we solved some problems from the seepage topic, and we saw what seepage is, and after that, we solved some problems from the in situ stress topic, right? So, we understood what is effective stress, what is total stress, and what is pore water pressure. After that, we solved some problems regarding those things. So we had layered soil, and at various points we determined the total stress, the effective stress, and the pore water pressure. So if you can recall a bit, if you remember, effective stress is nothing but total stress minus the pore water pressure. So effective stress is the stress that is actually taken by the grain to grain contact in the soil, right? And total stress is nothing but the total stress, from the word only you can understand that. And pore water pressure is the water exerted by it's the pressure exerted by the water that is in between the soil pores, right? That is in between the soil particles. All right. So this effective stress concept is actually very important because most of the strength equations, and what to say, this failure theories, all those things are actually based upon the effective stress concept. All right, all these things are based upon the effective stress concept. Okay, now we will be seeing that we will be using this effective stress concept in the consolidation topic too. So when we study the consolidation topic today, we will see that this effective stress, okay, this effective stress is also very much, what to say, it's very much important for this consolidate to understand the consolidation process. All right. So in today's session, what we will be doing is that we will be revising whatever has been taught in the previous in the theory classes as usual, and after that we will be solving some problems. Mostly the problems will be dealing with the topic of consolidation. Again, I would like to repeat that consolidation is actually a very important topic in soil mechanics. All right, so consolidation is one of the most important concepts in soil mechanics. So I suggest that all of you please go through this topic very nicely, and if there is any doubt at any point, please feel free to ask me. Okay, please feel free to ask me by interrupting me at any point of time, because this concept of consolidation is extremely important to us. All right, so let us start. Before we start consolidation, one of the small topics we will be discussing at the beginning, that is capillary rise in soil. All right, we will be discussing the capillary capillary rise in soil. So what is capillary rise? So you might have noticed while drinking a cold drink or some juice from a glass, when you put a straw in the glass, automatically some amount of cold drink or the liquid enters the straw, enters, and it rises up to the straw. Before you suck through your mouth, okay, just by just the moment you enter the straw into the liquid, what happens? Some of the liquid gushes into the straw and rises up the straw, right? So that concept is nothing but the capillary rise. All right, so the rise of liquid in a tube, when liquid in a tube, when the tube is inserted into the liquid, okay, liquid mass, that is known as the capillary rise. So now so you have seen this in case of straw, water in straw, right? When you put straw in water or in liquid, the liquid rises up in the straw. Now if we imagine the void spaces in the soil, if we imagine the void spaces in the soil as some capillary tube, Okay, so there are various interconnected pores are there in the soil mass, right? So there are interconnected pores in the soil mass. So these interconnected pores in the soil mass, or the void spaces in the soil mass, they actually behave as capillary tubes. Okay, so what happens? Water, say you have a soil mass. So you have a soil mass. Let's say you have this. This is a soil mass, and the water is here. This level, this dotted line represents the water table. So what happens due to the capillary reaction? The water rises to some height above the water table. Okay, this is due to the capillary action. Okay, this is the capillary rise. So if you remember, we had solved some problems but the capillary height, this HC was given, and that place we saw that the pore water pressure is actually negative. That is, there is suction that is developing here, and due to that, what was happening? The effective stress was increasing in this region. Okay, so this happens actually. All right. So yeah, so you can see a diagram is given here. So so we have water, right? We have a water. Say we have water here, and we have a capillary tube. So what happens? As I said, as we enter the tube into the water rises up through the tube. So that height of capillary rise Hc is actually given by this equation. Hc is equal to 40 cos alpha by d gamma w. All right, where E is nothing but the surface tension. E is nothing but the surface tension of water. Alpha is, you can see, alpha is shown here. Alpha is the angle. D is nothing but the diameter of the rod. And so you can see if D is less, okay, if D is less, smaller the diameter of the capillary tube, higher the water is going to rise. Okay, if D decreases, H is obviously going to increase. So you can see here for pure water and glass, alpha is actually 0. So you can write 40 by d gamma w. All right. Now in soil, okay, in soil the capillary rise, this is actually given by Hazen's formula. So Hazen, after conducting various experiments, he actually gives this relation where the capillary rise is given by C by E d10, where C is a constant, d10 is nothing but the effective size. Okay, if you remember, d10 is also called the effective size. Okay, this you can get from the grain size distribution chart. Effective size, d10 size, and E is nothing but the void ratio. Okay, okay, so lower the effective size, you can see higher it will be the height of the capillary rise. All right, so lower the effective size, higher will be the height of the capillary rise. Now, if you recall the problem from last class, we had discussed about effective stress in the zone of capillary rise, right? So this is the soil mass, this is the soil, and water table is this one. Okay, but what happens? Water, as I said, water will rise up due to capillary action to this height HC. Okay, this is HC. So what happens at this point? At this point, the pore water pressure is minus HC into gamma W. Okay, the pore water pressure is actually negative. So what happens actually? The effective stress is what? Total stress minus pore water pressure. So what happens? The effective stress actually increases due to the suction. Okay, there is a suction that is acts here. Okay, due to the suction, the effective stress increases. Okay, so what happens? These are the pores. So whatever there is a suction, opposite. Generally this is the pore. Generally pore water pressure acts like this, right? But here it's acting opposite. There is a suction. So this is a suction. What happens? All the grains will be coming more into contact with each other. So now you can understand, right, why this effective stress is increasing, right? So more into contact with each other means the grains are more with contact with each other. That means the effective stress is obviously going to increase, because that is what effective stress is. the stress transfer from grain to grain contact, right? Now in case of partial saturation, if the soil is not completely saturated, so this is the relation, okay, where we have this degree of saturation here. Okay. Well, that was all just a small topic. Now let us come to the main thing. Okay, now let us come to the main topic. Okay, now let us come to the main topic, which is nothing but consolidation. Okay, consolidation. Now, what is consolidation? So let us first discuss what consolidation is in simple terms. Say you have a soil layer, say you have a soil mass. That soil mass is completely saturated. Okay, so the main criteria for consolidation to occur is that we consider the soil should be 100% saturated. Alright, so for consolidation to occur, we consider that the soil is completely saturated. Okay, so remember it is 100% saturated. The soil is 100% saturated. So we have a soil mass. Alright, so we have a soil mass that is 100% saturated. Alright, so we have a soil mass that is 100% saturated. Now you know that generally for clays, so consolidation settlement, okay, generally occurs in consolidation. This phenomenon generally is described in the case of fine grained soil, that is clay soil. Why? You will say why? So now let us, before discussing this fine grained soil, let us just understand the scenario in case of coarse grained soil, such as sand. So in sand, what happens? Sand is saturated. So sand, what will happen? Sand, the pore sizes are larger, and you know for sand the coefficient of permeability or the hydraulic conductivity is large. So what? Very large compared to clay, it is very large. So what happens? Whenever water is there, the sand or the coarse grained soil easily lets water to pass through it, easily lets water to drain through it, right? Easily. So intuitively also you can imagine, right? So you have a sand, you pour water, easily the water passes through the sand. But what if the soil is a clay, that is a fine grained soil? Clay. What if the soil is a clay? So in clay, what happens? Say the clay is saturated. So in a saturated clay, what happens? The pores are very tiny, and that's why hydraulic conductivity of clays are very low. Right? The hydraulic conductivity or the coefficient of permeability of the clays are very low. Yeah, it's very small. So what happens? The water takes extremely large, a long amount of time to pass through the pores. So water, okay, so water, if you pour water into clay, what will happen? In order for the clay to pass all the water through it, to drain out all the water through it, it will take a very large amount of time, isn't it? It is going to take a very large amount of time. Why? Why is it going to take a very large amount of time? Because why? Because the coefficient of permeability or the hydraulic conductivity of the clay is very low. Alright, the hydraulic conductivity of the clay is very low. Alright, so that is the reason. Okay, so that is what is written here. So the elastic settlement, the first line is elastic settlement occurs immediately when there is an increase in steadiness in a saturated clay layer. So in a saturated clay layer, say you have a saturated clay layer, you apply some load. So immediately, as soon as you apply some load, there will be some immediate settlement. Okay, elastic settlement. It is called elastic settlement or immediate settlement. Okay, that is, remember this term, elastic settlement or immediate settlement. So as soon as we apply load in a clay layer, immediately as soon as we apply, some settlement will be there, or some settlement you understand, right? Some settlement will be there. Okay, some settlement of the clay will settle immediately a little bit, that is the elastic settlement. Okay, now let us understand next what we do. The hydraulic conductivity of the clay is very small, right? As we discussed, water takes long time to come out of the pores. All right, now what happens? as water takes long time to come out of the pores, as a drainage phenomenon in plays very time taking process, whenever you apply load, elastic settlement will occur, and what happens, that load actually generates excess pore water pressure in the soil. So the soil is saturated, right? We apply the load, elastic settlement will occur, and as soon as what will happen, that load will increase the pore. The water is there inside the pore of the soil mass, right? Water is there. It is not. It won't be able to get completed. It won't be able to get out of the soil mass in that small instant of time in which you are applying the load, isn't it? In the small instant of time in which you are applying the load, the water is not going to come out of the soil, because why? Because the hydraulic conductivity of clays is very small, and that's why water takes very long time to come out of clays, drain out of clays. So the water which is there in the pores, what will happen, some excess pore water pressure is going to get generated. All right, so excess pore water pressure is going to get generated. Excess pore water pressure is going to get generated. Okay, so water is there, so as soon as you apply the load, that load actually generates excess pore water pressure in the soil. That load generates excess pore water pressure in the soil. Now, as time passes, long time. So as I said earlier, this water takes long amount of time to pass through clays. So as time passes, as say 1 day, 2 days, 1 hour, like this, as time passes, slowly, this water is going to drain out. So as the water is going to drain out, what is going to happen is that this pore water pressure is going to get dissipated. That means the pore water pressure is going to reduce. Water is draining out, so pore water pressure is going to reduce. The pore water pressure is going to reduce, and at that instant, what is going to happen is that that load which was initially taken by the pore water pressure, that load is going to get transferred to the grain to grain contact. That is, it is going to get transferred to the soil granular contact. That is, that stress is going to come. That stress is going to appear now as effective stress, right? So as the pore water pressure is reducing, the pore effective stress actually keeps on increasing. Okay, and this phenomenon where there is drainage, where slow drainage of water is there, the excess pore water pressure keeps on reducing, and as the excess pore water pressure keeps on reducing, the effective stress is increasing. This phenomenon is accompanied by a certain change of volume in the soil or certain settlement. That settlement is known as consolidation settlement, or this process is known as consolidation. Okay, understood? So as soon as you have a saturated soil, let me summarize a bit. Let me summarize a bit. So you have a soil mass. As soon as you apply the load, some immediate settlement is elastic settlement is going to occur. Now the load that you have applied, that load is immediately going to get transferred to the soil mass, and that will get developed as excess pore water pressure, right? Now as time gradually passes, this water is going to get drained out, and this excess pore water pressure is going to get reduced. This excess pore water pressure is going to get reduced, and this excess pore water pressure is going to, this stress is going to get transferred as effective stress, get developed as heavy, the effective stress is going to increase. So this complete process is known as consolidation. So in this process, what happens, the volume of the soil reduces means that there is some settlement of the soil. Okay, and this process is known as consolidation. All right, so consolidation continues for a long time after the immediate settlement. Okay, it takes a very long time. Now, if you see the spring cylinder model, so whatever is we discussed, it is very easy to understand using this spring cylinder model. So original, so you can see here one spring is there. Okay, one cylinder is there. Inside the cylinder, you have one spring, and here we have, okay, we have a spring, and here we have water. Say, so now you can see here valve is closed. This valve is closed. Okay, this valve is closed, and this valve is closed. This is the original state. Now what happens, you apply some load P here. So as soon as you apply that load P, what is going to happen, that load is going to get developed as pore water pressure here. You can see P by A. This load is going to get immediately get transferred to this liquid here or water here and get developed as a pore water pressure. Now, now what we do, now we open this valve. So if you open this valve, what will happen? We are allowing drainage to occur, so water will gradually start coming out. Water will get coming out. So as water starts coming out, what will happen? This pore water pressure keeps on reducing. Okay, this pore water pressure keeps on reducing. So finally a state will come when this pore water pressure completely reduces, and you can see the spring has compressed. It is thus now the spring has taken all the rocks. Now here the spring is analogous to the effective stress or the grain to grain contact. Okay, understood, right? So initially the valve is closed. Okay, as you apply the load, whole load is getting transferred to the water as, and it gets developed as pore water pressure, right? The spring is not taking any load now. Now as you open the valve, what happens? The water will start ejecting and the spring will start taking load. That means the effective stress is going to increase and the pore water pressure keeps on reducing. Okay, and at a later time when the complete water gets or complete water gets this now stage will come when this whatever excess pore water pressure that was developed, that is P by A, that excess pore water pressure becomes equal to 0. At that time you can see the spring has compressed to maximum. That is now all the load P that you have applied, that complete load is transferred to the spring, that is the soil skeleton. Alright, so this is the mechanism of the spring cylinder model. Okay, now let us see this image. So you can see here we have a sand layer at the top, we have groundwater table here, then we have clay layer here, and below also we have sand layer. So sand layer, so clay is bounded by two sand layers. Okay, top there is sand, bottom there is sand, top there is sand, and between there is clay layer. So this means what? The clay is sandwiched between two sand layers, right? The clay is sandwiched between two sand layers. The clay is sandwiched between two sand layers. So that means what? This means nothing but, this means that this clay, okay, so what, so what, so this sand layer, what sand layer means, what sand layer means, what say the water in the clay layer will actually be able to drain out in both ways, at the top also, at the bottom also, right? Water as so sand is a sand acts as a drainage layer, so sand easily allows water to pass through it. So what will happen? The water that is there in the clay will be able to pass through the sand. Now you see we're applying a stress of delta sigma. This much stress you are applying. Okay, this much stress you are applying, and this is actually under water, so complete scenario is saturated. Okay, so as soon as you apply this stress, what is going to happen? All the, so now we are, now our focus should be only in the clay layer. Okay, so what is happening in the clay layer? This is our main focus. So as soon as we apply this stress delta sigma, what is going to happen is that the complete stress is going to increase the pore water pressure by delta sigma in the clay layer, right? So now let us see here. So this is at time t is equal to 0. So total stress, so you are applying this, so this is the total stress. So across the depth, complete depth, the total stress is this much, delta sigma. Now as I said, as soon as you apply this delta sigma, this is going to come up as the pore water pressure. So you can see this is come out as pore water pressure. So we are making three diagrams: total stress, pore water pressure, and effective stress. Okay, so pore water pressure, so all along the height of this, clay layer, the pore water pressure is increased to delta sigma. And what is the effective stress? The effective stress is 0, because at time t is equal to, as soon as you apply the load, all the load is going to be taken by the water, so effective stress is 0. Now at as time goes from t is equal to 0 to say t is equal to t1, okay, at any time instance say t is equal to t1, what is going to happen is that the water is going to come out from here, water is going to come out from here, so drainage is happening. So at these two extreme points of the clay, the immediate, so drainage is happening through these points. So at those points the pore water pressure is zero. Okay, those points the pore water pressure is zero. Okay, and you can see the pore water pressure diagram actually behaves something, comes something like this. Okay, something like this will be the pore water pressure. Okay, and what will be the effective stress? So effective stress will be maximum at the top, top and bottom, and minimum at the center. So this is the how the effective stress will be. And now at t is time, t is equal to infinity. Now at time t is equal to infinite, when all the water in the clay, okay, all the pore water pressure in the clay has been dissipated by drainage of water. By drainage of water, all the pore water pressure in the clay has been dissipated by drainage. What will happen? The pore water pressures will become zero, and the effective stress will be equal to what the this applied stress. All right. So this is the main concept of consolidation. Okay. Now, to understand this consolidation phenomenon, what we do is that we do a one-dimensional consolidation test. Okay, we do a one-dimensional consolidation test in clays. For a particular clay sample, what we do a test known as one-dimensional consolidation test. So let us see the test. So in the test, say we have the soil specimen. Okay, this soil specimen is there, and this complete soil specimen is kept between two powder stones, into powder stone, and this is completely submerged, so completely kept in a saturated condition. Okay, this is completely kept in a saturated condition. So what we do, we apply load, we keep, so say we apply some load, and at equal intervals of time we keep on taking the dial gauge reading. So one load is at least kept for 24 hours. Generally, it's generally kept for, each load is, say first you apply 5 kg load, so 5 kg load will be kept up to 24 hours of time. Okay, then we increase the load to 10 kg, and 10 kg load will be kept for 24 hours of time. So this is a time taking experiment. So this consolidation test is a time taking experiment. So what we do, we apply the load. Okay, there is a soil specimen, we apply the load, and we take this, keep on taking the dial gauge reading at at some specific interval of time. So what will we get? So we will see, we will solve some problems, that time it will be very clear. So what we get and what all this consolidation test helps us to guess, and how we get all those things, we will see this in the subsequent slides. Okay, just please wait and please have some patience for it. So the specimen size, so there are some specimen size, the particular size of specimen that you do. So generally the specimen size is 64 mm dia of the sample, and 25 mm thick sample. The load is applied to the specimen submerged under water. Each load is generally kept for 24 hours, as I said, and then the load is kept on doubling. So what we are going to get is that, what we find out from, so what our target, so our target is to plot these graph, void ratio versus, okay, void ratio versus effective stress in log scale. So this is the target, this is our target. Okay, from this test what we need to do, we need to get void ratio at each effective stress, that is at each load. Effective stress will get void ratio and effective stress. So like this we have to plot a graph. So this is our main target, this is what we need to get from the consolidation test. Okay, now a typical consolidation test graph actually looks like this. Okay, so okay, this is this is the deformation versus time graph. Okay, this one which is said, but this was the void ratio versus effective stress graph, and this is the deformation versus time graph. Okay, this is the deformation versus time graph. This is a different graph. This you can plot for each load. For each load you can, so for 5 kg you can have this graph, for 10 kg you can have this graph. So like this, for each load you can have this deformation versus time. So initially you can see, initial this part is known as nothing but the initial compression. Okay, so after that you can see this line is the main part where the main consolidation settlement is occurring, and after that this part is called the secondary consolidation. Okay, so the main important is this one. Okay, main important is this one, the primary consolidation. Okay, so consolidation test, we have an initial compression that is caused by preloading. So when you put the soil sample, initially some amount of dead weight is placed over that. Okay, that is called the preload is okay. It is known as the preloading. So initially there will be some preloading. After that we put the main weight. So due to that weight, this primary consolidation is going to get apart. That is known as primary consolidation. And the third stage is known as the, so in the initial compression there is some elastic settlement that is occurring. Okay, elastic readjustment, elastic settlement that is occurring. Okay, that is known as the stage 1, the initial compression. Then we have the actual primary consolidation where the pore water pressure gets dissipated and there is some volume change in the soil. That is the main primary consolidation part. After the primary consolidation ends, we have the last stage, that is the, that is caused by the plastic readjustment of the soil grains. That is known as the secondary consolidation. So main is our this primary consolidation. Now, as I said, we need to get the void ratio versus pressure plots, or void ratio versus effective stress plot. Okay, void ratio versus pressure plots, or void ratio versus effective stress plot. Now, how to actually get that? How to actually get that? So first thing we, so there, so I will now discuss some of the steps or some of the main things that you need to calculate. Okay, from the calculate so that you can get the void ratio versus pressure plots from the on the consolidation test. Okay, so first is the calculate the height of soil solids. So what is volume of soil solids? What is volume of soil solids? Volume of soil solids I can write as weight of solids by specific gravity of solids into gamma w. Like this I can write, right? This I can write. This I can write, isn't it? So now this divided by the area of cross section of the soil specimen will give me nothing but the height of soil solids, HS, right? So from this we can get the height of soil solids. Now initial height of void. So now what is volume of voids? Total volume minus volume. So what is volume of voids? Total volume minus volume of soil solids, right? Volume of soil solids, volume of soil solids. So similarly, the height of initial height of void is going to be nothing but H minus Hs. Initial height of the soil sample minus Hs, the height of soil solids. It is going to be by Hv. Now we are to calculate the initial void ratio. That is the void ratio at the beginning of the test. So what is void ratio? Volume of voids by volume of solids, that I can write as height of voids by height of solids. So height of voids you know, height of solids you know, both you had just calculated. Both you had just calculated. From there you can easily get this initial, right? Now for the first loading that you have made, the change in void ratio is given by delta is equal to delta H1 by Hs. So delta H1 is nothing but the change in height that you are seeing. from the dial gauge reading from the first loading. Okay, that is the H1. So delta H1 by Hs is going to be the delta E1. So now at that loading, so say you applied 5 kg load. That 5 kg load after 24 hours we have seen that. So initially the height of the specimen was 25 mm. Now the height of the specimen has reduced by 2 mm. So now it has become 23 mm. So delta E1 is going to be 2 by the height 2 by Hs, 2 by Hs. Alright, it is going to be 2 by Hs. Now at that point, at that instant, at the end of the 5 kg loading, you have to determine the void ratio. So that void ratio, how will you determine? E naught initial void ratio minus delta E1, right there. So you will get E1. Similarly, at each steps, what you can do, you can use the same procedure. So delta, what will be E2 for the next loading? E1 minus delta H2 by Hs. So similarly, like this, for each loading, what you can do, you can determine the void ratios. Okay, so we have the void ratios. Now you can get the void ratios for each loading. So you got the void ratio for each loading, and you have already have the pressure for each loading. So now you can plot E versus the pressure plots, void ratio versus pressure plots, right? This is one method. Another method is this change in void ratio method. So here what we are doing is that we assume that the obviously the soil sample is completely saturated at the end of the test, and what we do, determine the final void ratio. So what will be the final void ratio? E is equal to Wf into G. So S is 0, S is 1, right? Completely saturated. So E final is equal to water content at final into G. So water content at final you have to measure. So after the test is over, what we do, you take the sample from there, you take some amount of soil from the set sample, and you do the water content test, and you find out the water content. So that will be Wf. It is nothing but the water content at the end of the test. And G is nothing but the specific gravity of our soil sample. G is nothing but the specific gravity of our soil sample. Okay, specific gravity of soil solids, of the soil solids. So now what we can do, you know the final void ratio. Okay, done, that we know. Now what is del H by H? So del H by H, you can write delta E by 1 plus it is nothing but delta V by total complete volume. Right, so this can be represented as this. Okay, delta E by 1 plus E naught. Now the void ratio at the end of each effective stress can be calculated as E is equal to E minus delta E, where delta E is equal to H by HF by 1 plus EF. So this is one more method how you can calculate the void ratio at each step. Okay, so when we solve problems, this is going to be actually clear to you. All right, so at the end of each effective stress, E is going to be E naught, the initial void ratio, minus delta E. And what is delta E? Delta E is nothing but this. Delta E is by HF 1 plus EF. Okay. Now, what is normally consolidated and over consolidated soil? So there are generally two types of soil. Okay, normally consolidated soil and over consolidated soil. So normally consolidated soils are those say have a soil mass. Okay, so you apply, say first you apply 5 kg load in that soil mass, then you apply 10 kg load, then 20 kg, like this we apply up to 100 kg load. So that state, so 100 kg load, that 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 100 kg load is the maximum amount of load that soil has encountered in its history, right? 100 kg load. So in that state, the soil is normally consolidated. Okay. Now what we do, you keep on reducing the loads. Now from 100 you make it 80, then you make it 17, then you make it 60. Now what is the load in that soil? The load in that soil is 60 kg. 60 kg load you are putting on that soil. But initially how much? So before, is 60 kg the maximum amount of load that soil has encountered in its lifetime? No, right? In its lifetime, the soil has encountered a maximum of 100 kg load. But now I have reduced to 60 kg load. So this type of soil is known as actually over consolidated soil. So this over consolidated soil and normally consolidated soil can be actually understood by over consolidation ratio. So you can see this OCR, over consolidation ratio, is given by maximum applied stress in the past divided by present applied effective stress. So for normally consolidated soil it is generally 1, and for over consolidated soil it is generally greater than what? Greater than uh, for normally greater than 1. Okay, for over considered soil it is generally greater than 1. It is always greater than 1. OCR is greater than 1. So why it is greater than 1, you can see, right? So present applied stress will always be less than the maximum applied stress for over consolidated soil. Now if the present is equal to the maximum, that is normally consolidated, and if the present is more than the previous, then also it's normally consolidated. At that time NC will be less than 1, much less than 1. It's under consolidated. Okay. So these are just some mathematical concepts. So this is also very important to us. Over consolidation ratio. Okay. So if I say 100 kg, so you have a virgin soil mass. You have a soil mass. You have in your table you have a soil mass. You put 5 kg weight, 10 kg weight. You go up to 100 kg weight. Now at that point, 100 kg is the maximum amount of load that soil has encountered in its lifetime, right? So now what is the OCR? OCR is 1. Maximum applied stress in the past is also 100. Present applied effective stress is also 100, isn't it? So OCR is 1. That means the soil is normally consolidated. Now you remove the 100 kg mass and you put 50 kg mass. What will going to happen? So now what is the maximum applied stress in the past? It is 100. What is the present applied effective stress? It is 50. What is the maximum applied stress in the past? That was 100. But now what is the present? That is 50. Now that is what is the OCR? OCR is 2. That is the soil is OCR is greater than 1. That means the soil is over consolidated. Now I apply 120 kg. Okay, now if you compare it with 100 kg barrier, now this OCR is going to be less than 1. So soil is normally consolidated. Okay. Now let us see some important terms, actually important terms related to this consolidation. They're very important terms. So what is coefficient of compressibility? So what is coefficient of compressibility? Coefficient of compressibility is nothing but the slope of the void ratio versus effective stress or plot. Okay, so uh, for normally consolidated soil, the void ratio versus effective stress plot is something like this. Okay, so the slope of this E versus this effective stress plot is nothing but the coefficient of compressibility, AV. Okay, nothing but the coefficient of compressibility, AP. Okay. AV. Next we have compression index. So compression index is nothing but the slope of E versus log of effective stress graph. So for normally consolidated soil, it will be something like this. For normally consolidated soil, it will be something like this. Okay, so that is known as the compression index. Another term is MV, the coefficient of volume change or coefficient of volume compressibility. This is given by AB by 1 plus E naught. Okay, it's given by AB by 1 plus E naught. Then we have soiling index. Soiling index is delta or delta by sigma. Okay, this is the soiling index. And then we have the recompression index. So all these are various indexes. Okay, soiling index. Then we have the last. We have the recompression index. So this soiling, recompression, we will see what are these in the next slide. Okay, what is soiling, what is recompression? Okay, all these things we will see. Okay, so for NC is it is like this, and for OC it is generally like this. Okay, this is for OC. Now let me draw. Okay, this void ratio, this side we can put log of. So initially the graph is something like this up to a particular point. After that the graph becomes like this, straight. Okay, so this point is nothing but the pre-consolidation stress. Okay, so in this region the soil is over consolidated. Okay, pre-consolidation means what? Say the soil you have first applied 100 kg of load and then you have reduced it to 50 kg, and now from 50 kg you are start 100 kg of load you have plus applied and then you have brought it to zero. Now from that point you are applying the start you have started to do the test again. So now the initially the soil actually had in this history had encountered 100 kg, right? So this 100 is nothing but the pre-consolidation stress. So from 0 to 100 this soil is going to behave as a over consolidated soil. Now as the soil crosses this 100 kg mark, this is going to behave like a normally consolidated soil. Right? So this is known as a virgin curve. Okay, so we keep on increasing, we get a plot something like this. Now after reaching this point what we do, we unload it, we keep on reducing the load. So even if we reduce the load to zero, you can see that we are not able to reach this initial void ratio. Okay, you will reach this void ratio e1. E1 will always be less than e naught. We cannot reach this void ratio e naught. So there is some permanent amount of deformation that is going to occur. So this is the expansion for swelling swelling curve. Then we again load it, we have the recompression curve. So we have the recompression curve. Okay, so again after, as soon as we cross this point, we're going to get again like this. Okay, this is the, again the normally consolidated. So this is how the test diagram looks. This is the recompression. Okay, recompression. Okay, now I hope this swelling index and this recompression, all these things are clear to you. All right. I think this is going to E. All right. Okay. So now let us start. So these things actually I think all these things were discussed in the class. So still I thought that it will be better if I revise, if I just recapitulate everything once for you, right? So this will help you, like just freshen up a bit everything, and then what we can do now? Now we can actually start solving the problems. Okay. So first problem: compute the maximum capillary tension for a, just a second, compute the maximum capillary tension for a tube of 0.12 mm 12 mm in dia at 4 degree Celsius. Okay, so compute the maximum capillary tension for a tube of 0.12 mm in dia at 4 degree Celsius. So how can we do that? So if you recall H is what? E10. So this value of the C by E at 4 degrees actually given as, for water it is given as 3084 by D in centimeter. So this is in terms of soil, right? And this is in terms of, so any tube. Okay, So what is the D? It's going to come out as meter. Okay, therefore the F21. Okay. Okay, so this is not very important, just a simple problem. Okay, example. All right. Now the capillary rise in a soil having D10 size is given. D10 size is 49. So capillary rise is given. So in a soil having D10, there is the effective size is 0.07 mm. The capillary rise is 49 centimeters. Estimate the capillary rise in another soil having D10 as 0.12 mm. Okay, assuming same void ratios in both the soil. So now we have to use this size formula. So we have H is equal to C by E D10. So we can write that H into D10 is constant. H into D10 is constant in our case because C is constant, E is also constant. Right? So 49 into 0.07 is equal to H into 0.12. So here we can find out H, right? So please find out H. Let us see what H is in this case. So this size is increasing. So if the capillary size is increasing, but obviously the height is going to reduce, right? So let us see what the reduced height is. It will be 28.58. Okay, so you can see as D is increasing, H is reducing. Okay. Okay. So that was just a basic problem. Now let us come to the main problems dealing with this consolidation. Okay. So please read the problem once, go through the problem once, see if you can understand. See whatever it's given here, just try to go through the problem once. The following observations are recorded in a consolidation test. Initial height of specimen is 20 mm. Dia of specimen is 75 mm. Dia of specimen is 75 mm. The specific gravity of soil solids is 2.77. Final water content is given as 39%. So now final water content is given. So if this problem comes in a paper, comes in a question, so now you can understand that we have to use that second technique, right? The final void ratio technique. EF is equal to WF into G. That from there we have to keep on solving, right? So the initial height of specimen is given, diameter of specimen is given, GS is given, final water content is given. Now applied pressure. So you can see as we are applying the pressure, okay, the final dial gauge reading is given. The reading of the dial gauge is given. So you're increasing the pressure up to 800 kp and then you're reducing to 0. So all these readings are given. What we need to do, we need to calculate void ratio corresponding to each pressure increment. So you need to calculate the E value corresponding to each pressure increment so that we can plot the void ratio versus pressure plots. Right? That is our task. So how do you approach? How do we approach? So the first thing that we do is that, as I said, we determine the final void ratio. What was the final void ratio? EWF into GS. So what is WF? 39%, I think. 39%, it means 0.39 into 77. So please calculate this. How much is it coming? 1.08. Now initial height of the specimen is given as 20 mm. Now what is the final height? How to calculate the final height? How to calculate the final height? Now see how to calculate the final height. So what was the initial at zero pressure? The reading of the dial gauge is 100, and at end of the test again at zero pressure the reading of the dial gauge is 766. Okay, so from end first from beginning to end how much height change is happening, that how can we find out? And the dial gauge constant is given as into 10 to the power minus 2 mm, right? So how to calculate the uh, change in height from beginning to end, changing height? Isn't it? That is mm, right? Therefore final height is nothing but 20 minus 6.66 mm, that is 13.34. So what is this? This is the final height, that is our HF. Okay, this is the final height. Now if you remember, we need to find out delta E. So what is delta E? Delta H by HF 1 plus EF. So what is delta H? Delta H you don't know. So other things we can put delta H 1 plus. So delta H, for each delta H you will be putting it and we will be getting the delta E. Okay, we'll see that how to do. So this will come out as 0.156 delta H, and this is in mm. Okay, now what to do? Now let us make a table. Okay, now let us make a table. So first will be the pressure, then we have, let me just make it a little bit slicker. So we have pressure, then we have dial gauge reading, then we have delta H in mm, then we have H in mm, then we have delta E. What is delta E? 0.156 delta H, and then we have E is equal to EF minus delta E. This is where we will start from bottom. We will see that. Okay, so this is what we have. Okay, so initially P is 0, dr is 100. Let us write all the values. Okay, and how much? 899 766. Now you have to fill the delta H, that is the change in height. Okay, so initially 100, dial gauge reading when load is 0, it's 100. So 259 dial gauge reading is changing. So 259 matlab minus 2.59, right? Reducing, right? That's why I am putting minus sign. Height is reducing. 359 to 499, how much it's changing? By 140 means 1.40. 499 to 632. How much? Just a second. Yeah. 632 to 499 to 632. So minus 1.33. Then 768 from 632. So 632 minus 768 is 1.36. Like this, 899 from 768 minus 899, 131. That means minus 1.31. Okay, and at last 899 minus 766. It is 1.33. So this is the change in heights. Okay, at each, from each means each change in height. Okay, from here to here to here, like this, each change in height we are writing. All right. Now age. Now what is the age here? Age final, you know. What is the age final? 13.34. So here it's 13.34. Okay, it's 13.34. Now if this is 13.34, how much will be at 800? So 13.34 minus 1.31. So do it. 13.34, 13.34 minus 0.31 is 12.03. Sorry, 13.34 minus 13.34 minus 1.33. Right, so 12.01, like this. Okay, then 12.01, 12.01 minus of minus this. So 12.01, 12.01 minus of minus means plus 1.31, 13.32. Again 13.32 minus of minus 1.36, 14.68. Minus of minus 1.33, I will have 16.01. Then minus of minus, I will have 17.41. And so finally minus of minus, we will have 20. Understood? So like this you can go out from top to bottom also. Initial height you know 20. So 20 minus 20.59, 17.1. So like this also you can write. 17.4, like this also you can go. Your wish. I went from down to top, bottom to top. You can come from, in this case you can come from top to bottom also. Why bottom to top I have gone? Because here we will be writing everything from bottom to top. That's why we'll see that. Now what is delta E? 0.156 into delta H. So just multiply 0.156 with this delta Hs. So 0.156 into 1.33, 0.207. This is plus. Then my 0.156 into minus 1.31 into 0.204. Then into minus 1.36, 0.212. So this into minus 1.33, it will be minus 0.207. Done. We got this. Now the final void ratios how to get. Okay, so what is the final void ratio? 1.08. This you know, right? So write 1.08. 1.08. So same this 1.08 minus 0.207, EF minus delta E. So 1.08 minus 0.207, it will be 0.873. Now 1.873 minus of minus, that means plus 0.204, 1.077. Same plus 0.229. I did some mistake, huh? Yeah, done on right only, right? 1.496 plus 0.218. 1.496 plus 0.218. 1.714. That's right. This is 714. And plus this plus 0.404, 2.118. It's 2.118. So that's how we get it. Okay, so corresponding now, so now we have got corresponding to all the pressures, you have got it. So you can get this void ratio versus pressure plot. Okay, at pressure 0 we have 2.118 void ratio. All right, so like this you have to do it. Okay, so the more you solve these problems by yourselves, actually these things will be more clear. Okay, the more you solve the problem by yourself, the things will be crystal clear to you. So you have to do this by your hand, to do it yourself, otherwise it's very difficult. Just by looking by me doing it, it's very difficult. It won't get into your head. So I suggest that you solve this problem yourself, you practice this, so that each and every step actually becomes clear to you. All right, each and every step becomes clear to you. All right, so I hope this problem was clear to you. So let us move to the next one. Okay, the following observation are recorded in a consolidation test, each load being maintained for 24 hours, right, as usual. So for the consolidation test we have to do this, each load we have to maintain for 24 hours. Okay, that's the thing we have to do. Okay, the following observations are recorded in a consolidation test, each load being maintained for 24 hours. GS is given. Okay, the final water cut is almost same. Here what is given to you, the sample thickness is given. Okay, directly the sample thicknesses are given to you. Okay, so same we have to calculate the void ratio at each step. All right, so first again, what will be the first step? Please tell me, what will be the first thing that we need to determine? Please tell me. You already know, just now we solved this problem. So please tell me, what is the first step that we need to do? What is the first thing that we need to do? What is the first thing? The first thing is we need to determine the final void ratio, right? We need to determine the final void ratio. Correct? Right? Therefore, correct? So this will come out as 0.762. Now, Now let us use the what we can do. See, now del H by HF, you know, we can write as delta E by 1 plus EF, right? So now what is delta H? Okay, so uh, let us come from here to here, okay, from the end. So this delta HF is 13.90, right? So delta H will be 13.90 minus, sorry, 18.90 minus 18.36. So if we do this, we can get delta ES mm. Therefore, E1, what will be E1? So E1 will be EF, means 0.762 EF in case to reduce. So 0.762 minus 0.050 will give us 0.712. Alright, so we got corresponding to this, we got, so this one you knew already, right? This one was 0.762. So for this we got this 0.712. Similarly for this we can find out how either you can take these two or these two. So these two only I will take 800 400. So let us see delta H. What is delta H? What, let us take these two only. Let's take these two. So 0.90 0.762. So delta E is going to come out as, please see how much it comes. Let me also calculate. Just give me a second. 0.5. So E2 is going to be 0.5. Mm, 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 mm. Did I do some mistake? Wait. We cannot do it like this. See, what we need to do is that we need to take these two only. So if we take these two, 11 18.36 minus 18.56. See, I have written all these things wrong. See, this is plus only. This is minus y minus. Yes, you are writing it as 18.36 minus backwards, right? 0.36 by 18 point. So delta E2 is going to come out as 9. Okay, so let us make a table and see like this. It's actually really, I am also getting confused. Okay, so let us make a table, then it will be clear. Mm. Okay, then H. What is H? H is given, right? Now let us calculate delta H. So this is reducing minus 4 from here to here. It is reducing by how much? 0.4. Then 0.15 from here to here, 15 and 130. Here to here 0.29. Here to here 0.20. Here to here point. It's increasing plus 45. Okay. Now delta E. So for this we calculated delta E is 0.050. We calculated it. Now for second one, what will be the delta E? It's 0.019. This. Okay. Correct? Correct? Now next again how to do? So these two distributed, these two we got this. Right? So what for next one how can we do? Will be 18.85 minus 18.56 divided by 18.56 to delta E by, so E equal to E minus delta E. So here it is 62 0.712. Alright. Okay, like this we are going. Okay, 0.712 like this. If I go 31. Alright, so now for this one let me write the delta E. So 1 plus 731 it will be 31. From here I can get delta E as 7, so 0.027. So this is going to be 0.758. Okay, 19.15 minus 18.85 by 1.15. 18.85. Sorry. So from here again we'll get a E. Like this we need to calculate, okay? Like this we need to calculate. So the next one will be 0.035. Okay, so just take two pairs and then keep on calculating, okay? Because our relation is something like this, okay? Delta H by H is equal to delta E by 1 plus E. So from here we are finding delta E. So delta H is, what is delta H? Delta H is present minus the next. Like this you can do. Tell present minus next, present minus next, present minus, I will write it here. So delta E is delta H is present minus next by present. Do 1 plus E present. Like this we need to do. Okay. So again we get all the E values. Again we can plot and find out. So this is sometimes it's very, that's why I said it, this one you have to do by yourself, because I also got confused in this one, so it's very confusing and you can make mistakes very easily. It's a little bit very confusing. Okay, so that's why you need to practice this one very properly, else you will also mistake. So easily I also make many mistakes now, so that's the same thing, you are also very prone to mistakes in this case. All right, so please please solve these problems properly yourselves once, okay? It's important also. All right, and you can always going from bottom to top. All right, so if you understand how what you are doing, what thing you are doing, uh, you cannot be wrong. So you see, so first you know this, so now the stress is increasing at this level. So stress is obviously whatever void ratio I have, that void ratio should be less than this, so obviously this should be minus. So there, so like this if you always think na, then you won't make mistakes in signs also. Sign also you won't make any mistake. That's the thing. Okay, that's the thing. Okay, next minus present by present equal to delta E by 1 plus E present. So this is the formula. If you use this, okay, not this. This is not correct. This is correct. Next minus present by present. Alright. Now let us see this. In a consolidation test, the void ratio of the specimen was 1.052 under the effective pressure of 207 kN per meter square, changed to 0.932 when the pressure was increased to 430 kN. Calculate the coefficient of compressibility, coefficient, the compression index, and coefficient of volume compressibility. Now, please tell me what is coefficient of compressibility. Please try to recall what is coefficient of compressibility. So these are very confusing. Coefficient of compressibility, compression index, coefficient of volume compressibility. All these things sound very same to us, right? So these are a little bit confusing to us because all of these actually sound very much same, right? Very much this all these things sound very similar to us. So that's why these things should be clear. Which one is coefficient of compressibility? Which one is compression index? Which one is coefficient of volume compressibility? These things should be clear. Okay, all these things should be clear. So what coefficient of compressibility is nothing but AV is minus delta E by delta pi. So how to calculate? So what is the unit? What is the unit? Meter square per kilonewton. Opposite of this one. Reciprocal of this is this unit. E has no unit. Only delta's unit will come. Delta sigma stress unit will come. Opposite of stress unit meter square per kilonewton. Now what is compression index? CC. Compression index is okay. Sorry. Does this have any index unit? No, because it is an index, right? No unit. And now coefficient of volume compressibility MB. So AV you know. So initial void ratio you can take it as 1.052. What is the unit? Same as that of AV. So this MB, why is it known as coefficient of volume compressibility? Can you tell me why it is known as coefficient of volume compressibility? Because MB is nothing but the ratio of the change in volume to the change in effective stress. So this one we can write like this, right? And this one we can replace by, and what is this by this? Nothing but AV. So that's the thing. Negative sign, see, negative sign is coming from the negative slope. You remember, okay? That as the slope is negative, reducing, increasing stress is reducing. That's why negative. Okay, that sign is important, but not that important. Like you should know why this sign is coming, but don't get confused. Okay. Okay. Let's see this. For a flexible foundation with two sides, 2 meter and 3 meter, and an axial load of 750 kilonewton, determine the elastic settlement under one of corners. The soil position ratio is much, and Young's ratio, Young's modulus is much. Use IT as 0.7. Okay. So this elastic settlement is actually derived from the elastic theory. The expression for elastic settlement is actually derived from the elastic theory. All right, and this I is nothing but the this uh, a factor which is used to uh, say that where the settlement is occurring. Okay, this that I factor actually relates to that thing because When settlement occurs, so some so the so settlement occur, what happens is as the foundation is flexible, the foundation will settle might settle like this. Okay, so settlements are not equal everywhere, so that's why this vector is used. Okay, so how much pressure you are applying? 750 kilonewton load, so 750 divided by 3 into 2 to 125 kilonewton per meter square pressure you are applying. So what is the immediate settlement? Immediate settlement is given by QB 1 minus square is by, so 125. What is the width? The width is 2.37 square by 9.8 into 10 to the power 3 kPa to 0.0. So this one will come out as 115.41 meter, which is nothing but mm. Okay, so just directly you have to use the relation of the formula and find out the values. Okay, let us see the next problem. A standard soil has a compression index of 0.28. Its void ratio at a stress of 12 kPa. Its void ratio at its void ratio at a stress of 12 kPa is 2.05, and its permeability is 3.5 into 10 to the power minus 7 mm per second. So you can see how low the permeability of a clay is. Compute the change in void ratio. The stress is increased to 21.6 kN per meter square, and the settlement in the above case, if the stratum is, so you need to first you need to determine the change in void ratio, and then you need to determine the settlement that is occurring. The compression index of the soil is given. Alright, so now what is the compression index? If you can recall, what is it? Just now we calculated two problems back. Compression index is nothing but right. So we put 0.28 here, delta E log 21.65. So from here I can get delta E, right? So please calculate delta E fast, and after you calculate delta E, it will be 2.05 minus delta E, the changed new void ratio, because obviously we are increasing the void ratio is going to reduce, right? So please find this out. Please calculate in 2 minutes. Fast, very easy. Please calculate. So what is delta A? How much you are getting change in this change in word ratio? Coming at 0.07. So you can get 2.05 minus 0.97. Alright, so calculate the change in word ratio and the new word ratio, both you calculate. Now you have to find out the settlement. Okay, now you need to find out the settlement. Okay, now can you now see delta H by H can be written as delta E by 1 plus E naught. Now this delta E I can replace by Cc log, right, by 1 plus E naught. So delta H is what? Change in height. This is what? Nothing but a settlement. Nothing but HCC1 plus E naught log 10 by delta 1. So like this we can calculate the settlement. So settlement is nothing but H naught CC1 plus E naught log it. So H naught we know that is the thickness of the stratum, that is 6 meter. Okay, everything we know except we don't know Cc. So Cc we can take as 0.54 E naught minus 0.35. So yeah, Cc also we know. Cc is given, right? I think. Yeah, Cc is given 0.28. Cc is given. E naught we don't know. These all these things we know. E naught we don't know. So in order to determine E naught, what we do? Cc is given. Cc is given as 0.28. So from here you can get E naught as 0.869. So this is an empirical relation. Okay, empirical relation. So from here now I can put 6 into 0.28. This will come out as 0.229 meter to 9 centimeter. Okay, so this is how we calculate. So we calculate. So E naught is not known, initial void ratio, so I calculated Cc. Okay, Cc I calculated, and from there we uh, found out E naught, and then E naught we put, then we calculated. Okay. Okay, so this E naught is mean. Now let us see the next one. For the given soil profile, calculate the settlement due to primary consolidation for the 6 meter clay layer, 6 meter clay layer due to surcharge of 100 kPa. So here you can see sand is there at the top, clay is there, the bottom rock is there. We have a clay layer, so the water in the clay can drain out through the sand. That's why consolidation element will occur. Okay, so we need to calculate this primary consolidation element. Okay, the primary consolidation element we need to determine. So 100 kPa we are applying surcharge. So due to that 100 kPa, how much? You need to find out how much change in effective stress is going to come at the center of the layer. Okay, so so just to get an average, just to get an average change in effective stress at the layer, what we do? We find out at the center. We find out at the center. So at the center of the clay layer, we need to find out what is the this one, delta sigma. Okay, we find out the delta sigma. So this delta is how much? Now first let us uh, calculate all the effect unit weights. Okay, so first this dry for sand is what G comma W. G is 2.66. All these values are given in the figure, right? From here I can get 15.17. Next I have this given, saturated is given, so thus I deduct 9.81. I will get submerged unit weight. Now you need to calculate the effective stress at this point. So for that, please recall the in situ stresses part. Please recall the in situ stresses chapter. Please recall the in situ stresses chapter in order to calculate the effective stress, initial effective stress at this point. How to do? Initial effective stress. How to calculate? How to calculate? Please tell me. How to calculate? 4 meter into 15.17 plus submerged unit weight. How much? 9.556 into 3 meters, right? So this is going to give me the effective stress at that point. Effective stress at that point. Total stress minus pore water pressure. This is what directly I am calculating here, right? It will come out as 89.38. So initial effective stress, you know, change in stress, you know, that is 100. So you can calculate now the settlement due to the extra pressure of 100 that you are applying. Initial change, initial. Okay. So what is H? What is the thickness of the clay layer? 6 meters. What is CC? Compression index. What is the compression index? Is it given? See, it is not given. Liquid limit is given. So there is a relation between liquid limit and compression index. That is very important. Please remember this. Very important. Remember this. Okay. 009. Liquid limit is given as 60. 60 minus 10. It is 0.45. Okay. 0.45. What is the initial void ratio? 0.9. 89.38. So please calculate this fast. Please calculate. Let us see how much settlement is coming here. The clay layer. Let us see how much settlement is coming. How much? How much is it coming? 40. Yeah, 0.463 meter. That is 46.3 centimeter. Okay. So this much is the consolidation, primary consolidation settlement in this 6 meter deep clay layer. Okay. Okay, this is the amount of consolidation settlement that is going to occur in the 6 meter deep clay layer due to the application of an external surcharge of 100 kPa. Due to the external application of this 100 kPa surcharge, 46.3 centimeter of settlement this clay layer is going to undergo, right? Okay, now let us see this. In a consolidation test, thickness of saturated specimen of clay under consolidation pressure of 100 kPa is 25 mm and its water content is 15%. In a consolidation test, the thickness of a saturated specimen of clay under a consolidation pressure of 100 kPa is 25 mm. Okay, 25 mm is the thickness of the specimen and its water content is given 15%. On increasing the consolidation pressure to 200 kPa, the specimen thickness reduces to 23.5 after a consolidation. Obviously, if you increase the pressure, there is going to be consolidation settlement and the thickness is going to reduce, right? If the specific gravity of the clay is 2.7, find the compression index of the clay. So extremely easy. Please try to find this out. Very easy. Everything is given to you. Water content is given, so gravity is given, everything is given. You need to find out Cc, settlement is given, everything is given to you. Just you need to, the pressures are given, you need to find out the compression index Cc. So just a hint I will give you, use the settlement equation to find Cc. Everything just direct, I've told you, just do that now. Use the settlement equation to find Cc. I hope you can do that. Just try. Use the settlement equation to find Cc. Okay, use the settlement equation to find Cc. Alright, please do it. Please do it. Okay, please try. Very easy, direct question. Very direct question. Everything is given very clearly. See, what will be E? E is nothing but W into G as completely saturated. So W is how much? G is 2.7. So E I can get as 0.405. Now what is settlement? Consolidation settlement. Cannot. So how much settlement is occurring? 1.5. From 25 it is coming to 23.5. So 1.5. Cc I need to find out. What is H? Thickness 25 mm. 1 plus increasing to 200. So 100 200 is becoming from 100. Right. So just solve it and find Cc. Please find how much Cc is coming from this. Just solve it and find Cc. Very easy. So Cc will come out as 0.2. Okay, so directly all values are given. Just put, you need to think what equation you need to use, what proper equation you need to use. Just directly put the equation and find out the value of Cc. All right. Okay, clear. Now let us go to the 10th problem. A clay soil tested in a consolidometer showed a reduction in void ratio from 1.82 to 1.51 when the pressure was increased from 1.45 kPa to 220 kPa. Okay, a clay soil is tested in a consolidometer. Okay, consolidation test is done. The void ratio reduced from 1.80 to 1.51 when the pressure was increased from 145 kPa to 220 kPa. Calculate the coefficient of compressibility and the coefficient of volume compressibility, means AV and MV, if the soil site has a thickness of 4 meter. Determine the consolidation settlement to the given stress increment. Okay, there's two parts. First, you need to determine this coefficient, and then if the thickness of the soil is this much, you need to determine the consolidation settlement. So similar problem. So let us solve it. Same, almost same. So first is given, calculate the coefficient of compressibility. So what is coefficient of compressibility? It's AV. What is AV? Delta E by delta sigma 1. So please calculate. Very easy. Very easy, right? What is delta E? 1.82 minus when? 220 minus. Please calculate. Please calculate. Please calculate this. Let us see how much it is coming. Please calculate. So this one is how much? 4.13 into 10 to the power minus 3. Right. So what is the unit? Unit is how much? Unit will be meter square per kilonewton. Correct. Meter square per kilonewton. That is the unit. Okay. Now MV, AV you determined MV very easy. AV by 1 plus E naught. So AV you know. Just calculate it. Very easy. Same. Same. This will be same unit. So AV and MV you have calculated. Right. Now you are asked to determine the consolidation settlement. Okay, settlement you have to take. Now see, now these constants. So previously we found out the consolidation. Previously we found out the consolidation settlements when CC was given. That is the compression index was given. Now if we have the coefficient of compressibility or the coefficient of volume compressibility, how do we find out the consolidation settlement? See how to do that. So delta H by H is delta E by 1 plus E naught. So delta H is for nothing but the consolidation settlement. E naught, right? So settlement is H into delta E by 1 plus E naught. Now what is delta E? So again I am representing delta E. So delta E I can write it as AV into delta sigma. E naught. Now AV, and what is this? This is nothing but MV. So H into MV into, done. Very simple, right? So from here what we can do, we can calculate the consolidation settlement. So what is H? What is H? 4 meter. What is MB? 1.46 into 10 to the power minus 3 meters square per kilonewton. What is the change in stress? What is the change in stress? 145 to 220. 145 to 220. So 220 minus. So find it out. Simple. Very simple. Please calculate. Please calculate. Extremely simple. This will be 0.438 meter or 43.8 centimeter. Okay. So I hope you understood this. Very simple, again very simple. So this problem, consolidation problems are very simple. Alright, just for that those problems like where they are making the table and we're calculating the values for the plotting the E versus pressure plots, that to be very careful. That is a little bit confusing. So please practice that, then that will be fine. Otherwise, these settlement calculations, all these things are very easy, quite easy only. Alright. Okay, now let us come to this. This is the last problem for today. Let us come to this problem 11. For the footing arrangement shown in the figure, determine the consolidation settlement of the normally consolidated clay layer. Unit weight is given. So see, we have a sand layer. Below that we have a clay layer. Again we have a sand layer. So due to the sand layer, the water is going to get drained out from the clay layer. Pool water pressure is going to get dissipated, and due to distribution of pool water pressure, what are we going to have? We're going to have consolidation settlement. Right. So we have a footing, right? So 4,000 kilonewton we are applying on the footing. So let us calculate the pressure at the base of the footing. Okay, so what will happen? Some pressure is there at the base of the footing, and that pressure at the base of the footing, what we are saying is that pressure is getting will get distributed in 2:1, means two horizontal to one vertical, in this fashion this is going to get distributed. Okay, in trapezoidal fashion this stressor is going to get distributed, and this we at a depth at the mid of the, okay, at the mid of the clay layer we are going to find that value. So that will be our increased stress, increased pressure that will apply. Okay. Okay, first let us what can we do? First let us calculate. So you can see everything is under the groundwater table, right? Everything is under groundwater table. So everything is under groundwater table means everything is submerged. Okay, let us first calculate the submerged unit weights. Okay, submerged unit weights. So for sand it is given saturated is 18, so minus 10, 8 kilonewton per meter. And for clay, energy minus 1 plus W 2.65 minus 1 plus E as W 2.65 into 0.3143 to 10. Okay, so this will be 9 kilonewton per meter cube. Alright. Now what is the effective stress at the center mid of this clay layer at CC is the mid of the clay layer. What is the effective stress? Please find out. 7 effective stress will be 7.5 into 8 plus 1.5 into 9. This is the effective stress. Now the next task is to find out the increased stress. Increased stress from what? Increased stress coming from the footing, right? Increased stress is coming from the our footing. How to find that? So we are assuming that there is 2:1 distribution. So if there is 2:1 distribution, what we do, we can write it like this: Q by area, right? Q by area. So area B plus twice NZ, L plus twice NZ, where one vertical is to two horizontal. This you are assuming, right? So N is this 2. Okay, so like this if we write, we can write 4,000 by 1.5. So this is what? This is 1.5 by 1.5. So 1.5 plus 2 into Z. So what is Z? What is Z? So this is 3, and this is how much? 7.5 minus 1.5. So this distance is 7.5 minus 1.5. Means what? 6. 6 meters, 6 also 7.5 only, right? So into 7.5 square, as it is a square footing, so square, right? So this one will come out as 4.03 per meter square. Okay, just check it yourself once. Okay, check the values once. So same, now done. So now again as usual, so H is 3, cc. How to find out cc again you have to calculate. So cc is 0.8. It's given, actually it's given, directly given. 0.38 1 plus E naught is this 2.65 into 0.3143. This will be 1.05 log 73.5 plus 4.03 by 73.5. So this is going to, oh sorry, this E naught you have to calculate from here, cc. 0.38. If E naught is not given, you naught is calculated like this. So from this we will get finally SC is equal to, okay, so please check this one yourself. Okay, please check. this yourself. Okay. Okay, so done. So this was all for today. We solved some easy problems from this consolidation topic, right? So I hope it was fine to you. All right. So thank you so much for attending today's session, and with this we're going to end today's session. Thank you so much. See you next week. So next week, that is on the 8th. Okay, on the 8th of March we will meet again. 8th of March, from 6 p.m. to 8 p.m. we'll be meeting again. All right, 6 p.m. to 8 p.m. on the 8th of March. Thank you so much for attending, and have a very good day. Thank you. Thank you.